Well, good evening, everyone. Thank you very much for coming to the Royal Society. Just before we begin, a brief bit of housekeeping. If you hear a fire bell, there is no drill planned tonight, so please leave by the door you came in through. But otherwise, it's a very great pleasure to introduce your panel for this evening. Our host is Robin Ince. We have Anna Scaife, Laura Nuttall, Jon Butterworth, and Sarah Williams. So please make them welcome.
I'm Robin Ince, and some of my living is made interrupting the physicist Brian Cox on Radio 4 when he starts to confuse people, which means that I have to work very hard and talk a lot. And we're going to be talking today about big experiments, exactly what it says, giant experiments, and the fact that very often the enormity of these experiments seems to conflict with the smallness of what is being scrutinised. I went to CERN in January, and when you go, have any of you visited CERN? You will know it's very, it's weird in the comedy clubs, far fewer hands go up. But it is that remarkable thing of, as some people call it a cathedral when they first see it. I felt it was almost like Stonehenge, that, in 5,000 years' time, whatever civilization there is will go, what did they make this for? And how did they get the magnet so far? All of those things, that sense of questioning, that sense of magnificence. And I think something like, both the work that we've also seen on gravitational waves, the work that we've seen in terms of the Higgs field, all of those things I think have helped reignite the excitement in science. Because I have the CERN pop-up book. I don't know if any of you have the CERN pop-up book, the LHC pop-up book. And it is, have you got it?
No, but I want it for my son.
Oh, it's so good, right? Because it's a very complex pop-up book, so that when you open it, it doesn't open properly, and you have to all nudge it into place to make it work. So I felt it was very scientific. So I'm going to start off just by asking our panel to introduce themselves, give a little bit of a sense of what they're currently working on, and I'd also like them to answer this question in their introduction, which was, what was the first cosmological idea that really started to excite them, whether in childhood or whether afterwards? What was that first sense of whether the size of the universe, whether about the nature of time, the fabric of space-time, whatever it might be? So should we start over here?
Okie dokie. So hi everyone, my name's Laura Nuttall. I'm an Associate Professor of Astrophysics at the University of Portsmouth, and my area of research is gravitational waves. So at the moment, the LIGO, Virgo and Cagra detectors have just started their fourth observing run just 2 weeks ago. So we're looking for black holes and neutron stars that are colliding. You can keep track of what we're up to. There's plenty of stuff for the public to have a look at and get involved with, and we're detecting these things on the order of every few days now. So that's really, really very exciting for us. So kind of the thing that kind of got me into physics, I think I've bounced around. I can't say there's been a grand plan for me to be sat here today in front of you actually speaking about this topic. I think when I went to university, physics was I'm going to always be able to answer questions, I'm never going to get bored. But I think I remember in one of my first cosmology lectures, the idea that inflation happened, and it kind of happened at all points in space at the same time. And I was like, what? It doesn't go into something that idea of where does it go? What is space beyond that or something like that? And I think that was the bit that was right, I clearly want to go into some form of research. Not sure what just yet, but that's the thing that kind of sparked my imagination, just kept me asking questions.
See, that's the bit that gets me every single time, is when people say that even at the beginning, when the universe was expanding, it was also infinite at the same time.
Yeah.
And I think for anyone who's an arts graduate like me, and indeed, in fact, most scientists, that idea, it's like the idea of more than one infinity. Yeah. And it makes total sense when you read about Hilbert's Hotel and you realise that if you have an infinity and then you add one to your infinity and all of those things, but still, that, for any human being, infinity itself, I think, is pretty hard to grasp. And then to go, and there's not just one infinity to grasp as well.
Yeah. Yeah, absolutely. It's just all these kind of mind-boggling things, really, I think, that just keep us kind of going with it. And I only discovered gravitational waves kind of down the line in my university career. And it was just through a happenstance of an optics lecture where I just remember this professor just talking about this crazy contraption in Germany that was trying to measure ripples in the fabric of space-time. And I was like, ooh, that sounds interesting. And it just sounded just a little bit crazy enough, because then it hadn't been detected yet when I was an undergraduate, that it was just the thing that caught me, and that's the thing that I've kind of run with since.
Anna.
Yeah, okay. So hi, I'm Anna Scaife. I'm Professor of Radio Astronomy at the University of Manchester. I describe myself as a general purpose radio astronomer because I've worked on...
Everyone needs one.
Yeah, well, yeah, exactly. Funding councils.
Yeah.
But yeah, so I've worked on all aspects of radio astronomy, from galactic to extragalactic radio astronomy, building telescopes, designing telescopes, analysing the data from telescopes. That takes up a lot of my time. And these days, mainly what I do is design the artificial intelligence algorithms that will replace me. So, yeah. I never wanted to be an astronomer. When I was younger, I wanted to be an archaeologist. I was heavily influenced by Indiana Jones films. And then I saw Time Team, and it kind of brought me down to earth a bit. And
So hang on, I have to ask you, so what was it about Time Team? Was it the lack of bullwhips? Was it that, what was it in particular?
I think it was the tents in muddy fields. Yeah, it's like these are the archaeologists that have made it onto television, and yet they're still camping. So, yeah,
that idea of going, have you found the Ark of the Covenant? No, but I found this wonderful little piece of pottery, actually.
Yes,
We've only spent 3 years digging this field.
Exactly, yes. And so the glamour was somewhat lacking, I think, compared to Harrison Ford's life. But so then I finished my undergraduate degree, and I'd worked on an undergraduate project on astronomy, and I couldn't think what else to do, so I applied for PhDs. And at the time I literally said to myself, I will do anything apart from cosmology. And I ended up doing a PhD in observational cosmology. So I was an accidental cosmologist, and then I spent the rest of my career moving out of cosmology. But I discovered that I really enjoyed the stuff around it, if you like, the more technical side of astronomy, and that's brought me to where I am now. But much like Laura, yeah, it was unintentional.
So I suppose we should ask that question, but are you happy?
Are any of us truly happy, Robin?
Welcome to Philosophy 2.1, and don't worry, John, we won't do philosophy. I know what you get like with that. So, John, tell us a little bit about yourself, and also what is your first grand cosmological question.
Okay, so I'm Jon Butterworth. I'm a professor of physics. I'm local. I'm from University College London. And I work on the ATLAS experiment at CERN, so one of the Large Hadron Collider detectors that found the Higgs boson about 10 years ago. And I've been involved in that for a long time. I was involved when we were building it, and now I spend most of my time analysing data from it and going to meetings. Stay with me on the cosmological inspirational idea. It was the number of moons. So when I was little, I was about, I think, 9 years old. This makes me sound far more single-minded than I really am, by the way. But me and my brother, who was a bit younger than me, and a friend of ours, decided we were kind of into astronomy. It's always astronomy, right? We decided to write the definitive book on the solar system. And we started to write chapter headings. So we'll do Mercury, and then how did they go? Mercury and then Venus, and then anyway, that kind of thing, and the moons, and a little subchapter for each of the moons. And this was, I think, when Voyager was hitting Jupiter or Saturn or something. And anyway, every week we were having to add more moon chapters because they were finding more and more moons every day at that point or something. And it was really, frankly, I didn't care much about the moons, but it was the idea that there's stuff no one ever knew before that we know now. And I just thought, this is for me. I want to be the first person to know something. So it wasn't really a big cosmological idea. It was the idea of human beings exploring the universe we're in and finding out stuff that wasn't in any books. We didn't know that ever before. And then, to have the privilege to be one of the first people to see the peak of the Higgs boson in the data from the LHC was like, it's better than moons.
Well, that thing as well of starting with astronomy, I think it almost has to, doesn't it, in a certain way, because so much of what you're all working on is invisible, and it is something that, we see the night sky, we see, I was doing an event at a primary school, and afterwards this young girl came up to me and she went, "Excuse me, mister, I just want to say I saw a full moon yesterday, and it shines really brightly. Can I tell you, I know why it shines so brightly?" And it was like that excitement to watch that. Or the moon, on, what was it, last week on Friday, or Saturday, I think, seeing that but when you go, what first inspired you? Gravitational waves. You know, that's an unlikely thing. And if that is what first inspires you when you're 7 years old, well, you're going to have quite a career ahead of you. Or you're going to peak early, one or the other.
So why did that apple fall down? It could have been that, you know, it could be like everyday physics, but it hardly ever is it? It's only like, you come to that later. Yeah.
Sarah.
Hi everyone, my name is Sarah Williams and I'm an Assistant Professor of High Energy Physics at the University of Cambridge. I'm also on the Atlas experiment, like Jon, but I've actually spent a lot of the last decade searching for things we hope exist, but we don't know what they are, so I've done a lot of searches for dark matter. So my first cosmological experience in observation is a little bit embarrassing. I remember being pretty young, and my parents convinced me that a star moving across the sky was Father Christmas, and I duly watched it for quite a long time. And I think that was maybe the early sign that maybe studying the universe on the larger scale was not for me. I then, explored various other career paths. I wanted to be a politician, I wanted to be a lawyer, gave up on both of those. And then when I was doing science at university, I got the opportunity to go to CERN and do a summer student project. And this was about a year after the LHC had initially switched on and had problems with the magnets, so had to close down for repairs again. And I think for me that was kind of the thing that switched on the questions again, and I really wanted to kind of study the universe but on the smallest possible scale instead. So I guess I've been on Atlas for a while, but actually a lot of what I'm doing at the moment is trying to actually think about what comes after the LHC, which I'm sure we'll be talking about later on in this session.
That's interesting, actually, that for most of you, the inspiration came through lots of kind of different diversions. I don't know if it's an English thing, because I know that it's like the difference between American astronauts and British astronauts. Is American astronauts very often have this incredible backstory of adventure, and both Helen and Tim, if you ask them why they became astronauts, they say, I saw an advert. And it's kind of, that difference in this. Well, right then. And by the way, hello everyone at home who's watching as well. There's so much to... So I'm going to go to you first of all, actually, because I want to go further. Dark matter is one of those things where there's so many different levels of confusion. Scientists made a terrible mistake, of course, by having dark matter and then calling something else dark energy, which leads to a lot of confusion. So in terms of what you're trying to do and what you are able to use, the technology you're able to use, how are you investigating dark matter?
Okay, well, big question to start with. So dark matter, most broadly, is a type of matter we know exists in the universe, but we don't know what it's made of. And one of the really exciting things about the LHC is if we assume it does exist and has some kind of weak interaction with the particles we know about, then we should be able to produce it. So what I've been trying to do is use the high energy collisions in the LHC to actually search for signs that we could have produced dark matter particles in the collisions. Of course, looking at the way dark matter behaves in the universe, there are lots of possible particles that could explain what it's made of. All we know is it should be relatively weakly interacting. It needs to behave in the early universe such that structures can form, and we get the universe we see today. But apart from that, there are lots of different candidates. And so there are particular types of particles that if they were dark matter, we could see them at the LHC, but also, we have to, I guess, reconfigure our expectation that not finding them is actually still information that allows us to guide where we could search in future.
So why do we... when did dark matter come up as an idea? Why is it required for us to be able to understand the nature of the universe?
Oh, that's a good question. So I think it was back in the 30s, right, that Zwicky first said, who ordered that? So if you look at the behavior of the universe on a very large scale, from things like the rotational curves of galaxies, or now how light actually bends when moving through the universe, we have very strong evidence that essentially the amount of matter in the universe can't be explained by the types of matter that make up you and I. So, 5% of the mass and energy in the universe is atoms like we're made out of, then 25% is dark matter, and then the rest is dark energy, which I think the other side of the room are better placed to comment on. That's something that, as a particle physicist, I'm happy to pass the baton on. Dark matter we might get, dark energy no.
Yeah, we may well skip the dark energy bit because, how's it going?
Dark energy?
I don't really do much about dark energy.
Brilliant. There we go. That's all we needed. And I'll tell you what, you have now found out as much as almost everyone else knows at that moment. We're going to stick with the dark matter. Jon, in terms of your work, when did you first go to CERN? Because I obviously we did a live link up.
Yeah.
I remember when I was at Hammersmith Apollo and you were out in CERN and this incredible, what does seem to be the answer came, the first answer, Higgs field, the idea of that came much earlier than might have been expected. So can you explain a little bit about that experiment?
Sure, yeah. So well, Sarah already alluded to part of the reason it came earlier as well. So what did actually, Harry, do you want to put the picture of the LHC up?
Yay!
There. So this is what we're doing at CERN. This is the view you get as you approach Geneva Airport, really, over the Jura. Since we're in London, it's worth saying that tunnel, that yellow ring there, is a tunnel underground that's full of superconducting magnets, where we're colliding the highest energy beams of particles that we've ever had in a lab together, head on, counter-circulating. And like I say, since we're in London, it's good mnemonic. You can never remember how to say mnemonic, which is kind of ironic, really. But it's 27 kilometres round, which is the same length of the nearest kilometre as a circle line, which is why the line is yellow. And that's CERN over there, the main lab, and Atlas and CMS are the two, if you like, the two very fast, very high resolution digital cameras, if you like, which to take pictures of what happens when these beams collide. And so I was working, I did my PhD and my postdoc and the first work at UCL on an experiment in Hamburg, which was actually using electrons to look inside protons. So it was kind of a big electron microscope. It was a collider, but it was doing that. And then it kind of gradually moved to the LHC, where knowing what's in a proton was kind of useful, because now the proton was the tool you were using to try and make Higgs bosons and dark matter and whatever else might go on at these energies. So we were involved in building the Large Hadron Collider. We built bits of the detector of Atlas were built at UCL and in the UK. So I was involved in, it's like a huge international jigsaw puzzle, really. You've got to make sure it all comes, thank you. You've got to make sure it all comes together and fits together and works together, and it's being built all around the world. And that was quite exciting. And then we turned it on, and we had a very exciting Big Bang Day, where your friend Brian took BBC to CERN for the day, and it was huge, and the sun said the world didn't end, and it wasn't exciting. The secret is we never actually collided any particles on that day. We just got the beam to go around, which was a big deal, and everyone was very excited. And then 9 days later it blew up and broke, but then it came back again a year later. And when you say it was quicker than we expected, it was we actually only came back at half the energy, and we were kind of lucky that we could find it with a lower energy. Because of the incident, we were a bit cautious in building up the energy, but actually it showed up really early on. Very, very lucky. And so it was 2012 in the end where we kind of crossed the line. Do you want to play the video, or did you just play it? I missed it while I was talking. I can't remember. Yeah. So you see okay, there we go. This is the proton's view of making a Higgs, and this is the collision inside one of the detectors. So from those fragments, the Higgs boson itself doesn't live very long, but it kind of decays, it falls apart into other particles. But if you measure the energy and angle of those particles and things very precisely, you can reconstruct what where they came from. And in the end, do we have, actually I've forgotten, do we have the bump in here, the Higgs bump? Don't think we have that slide.
I don't think we do.
So just anyway, use mine.
Yeah, it's kind of like that. But you can measure the energy and angle and hypothesize there was a new particle. And if you do that, then you see an anomalous, it's another one of those words, an anomalous clustering of events around the mass of the Higgs. And that's a sign that there's something going on. And that's what we discovered. So that was all kind of, it was a bit of a blur, to be honest, from like 2008 when we turned on and then had the incident and then came back, fixed it and came back, and up to 2012. My daughter is now 16, and I feel that I missed a big chunk of her childhood because of that, to be honest. I mean, I regret that, but you know, she got over it. but it really isn't. No, I was around, you know, it's not that bad. But what I'm saying is...
You're really changing the angle of this show now. Please welcome Mrs. Butterworth. The doors slam open. Tonight's show is in memory of Jerry Springer.
Edie, if you're watching this video, it was great. There were great years, okay? But what I mean genuinely is a bit of a blur. It's kind of incredible to have been involved. I think Peter Higgs said it's incredible that this happened in my lifetime. Well, you know, those 4 years for me were just amazing, and that was, you know, having got the stuff you've been working on for so many years, to see it work, and then to see this fundamentally new truth about the way the universe works emerge from the data was, very special. It seems to have gone on a long time. Actually, Harry, do you want to put the map up?
We will get back.
Yeah, there you go. That's it. I'll let someone else talk in a minute. I'm sorry, but this is my illustration of what I think we're doing now. Right. So we found a Higgs here, and this kind of archipelago of islands is supposed to be what we think of as subatomic physics. It's what we know about subatomic physics. Okay. It's the electron gives you an entry to it. You find the nucleus inside of that. You find the protons and the neutrons, the quarks. In the end, we've been exploring this landscape through my whole career, through all our careers, and now the question we're asking really, is that it? Because the standard model doesn't predict any new particles now, apart from the Higgs. And on this map, as you go further east, you're going up in energy. And you see the Higgs is on the far east, and the top quark, the heaviest particles in the standard model there. And the way I picture us now is kind of sitting in a pub on the dockside on the east coast of Bosonia. And the theorists are telling us all this stuff that's out there. And what the Large Hadron Collider is still allowing us to do, it's allowed us to explore that bit of territory, and now I think of us in a little boat now, sailing further east and seeing what we see. The difference is that the theorists had they gave us a very good clue of what was on the island, that the Higgs was there. We had very strong reasons to know, and if we'd have gone there and found there was no island, that would have been almost more exciting than finding the island. Almost, not quite, but it would have been very surprising. Whereas now we have no guarantee what's out there, and if you listen to different theorists, they'll tell you different things. So there were a lot of ideas that we've already proved were wrong, and some of them involved in the kind of dark matter candidates that Sarah's been looking for. And I find this is just exploratory, and I really enjoy that sense of exploration, which I think is very much in common with building a huge radio telescope or looking for gravitational wave sources. We're not out there trying to prove a theory now, we're out there trying to just see how far we can push our understanding, and I really like that.
So in terms, I'm just looking at those, you know, basically the Here Be Dragons section of the map. How many of those do we think will actually end up merely being a myth based on a drunken sailor coming up with the wrong observation? We'll come back to that. Now, Anna, you are working at Jodrell Bank, so you're working now, sometimes in a very simplistic way. We might say that the LHC is looking inward and inward and inward, even though obviously that has tremendous ramifications. But I remember the first time of going to Jodrell Bank, and I remember standing in the middle of that telescope because someone had the keys and they let us in, and it was it's one of my favourite moments that I've ever had. I would say, going 100 metres underground at CERN was pretty incredible, but standing in that dish, there was something that it almost becomes mythic, and it almost becomes a psychosomatic sense that you can feel the waves, that you can feel what's being analysed, this interrogation of the universe. So can you tell us a little bit about what the work is that's going on now with radio astronomy there?
Yeah, so you can see in the picture the telescope that Robin's talking about, the Lovell telescope, and it is iconic. Right, the photo doesn't do it justice really because of the angle, but it's 76 meters across. It's huge. The side towers on it are gun turrets from a Second World War battleship. Right, it was built in 1957 and it's still the third largest fully steerable radio telescope in the world. It's absolutely fabulous, but and it is a fully functioning cutting edge scientific instrument. It makes measurements on its own. It gets integrated into arrays of telescopes around the world. But the other thing that's happening at Jodrell Bank at the moment is what's happening in the building that you can see in front of the telescope there. And this is the headquarters for what's called the Square Kilometre Array Observatory, which is the world's first intergovernmental organisation for radio astronomy. So it's like CERN for radio astronomy. except it doesn't have a tunnel. And it's the headquarters of an organisation that's building the next big radio telescope. Now, these days, it's not 1957 anymore. You need more than one big dish. So, thank you very much, Harry. So the radio telescopes we build now are not single big dishes, because you just can't make them big enough. It's not structurally possible to do the kind of science that you need to do with single dishes. So we build arrays of dishes, so multiple dishes, and we link them all up through very highly calibrated timing signals in order to combine the signals from the telescopes together, and they basically act like the equivalent of a dish that is as large as the biggest separation between two of those antennas on the ground. So the square kilometre array is going to put an array of dishes, well, two arrays of telescopes. We'll talk about the dishes first. So you can see on your left an array of dishes that looks like this, spread over 200 kilometres in the northern Cape of South Africa. And there'll be 197 of these dishes. And they basically act as if you've built a single dish that is 200 kilometres across. So it's like building a really, really giant telescope that wouldn't physically be possible. And we know it's not physically possible, by the way, because, some of the largest telescopes in the world have fallen down, which is slightly unfortunate. So we've learned that lesson. But the square kilometre array is larger than just one telescope, and that's what you can see on the right-hand side there, which probably doesn't look like a telescope at all to a lot of people. It looks like a collection of coat hangers in a field. But this is what we use for low-frequency radio astronomy, where we don't even build dishes because you need such large areas that it's just not possible. So we link up dipole antennas, and they act like dishes. And these two telescopes form the Square Kilometre Array Observatory, which will be the world's biggest radio telescope. It'll start operations in about 5 years' time. It's already being built, and the precursor instruments are already taking data. I think probably the one thing I would say about it also is that we really should have thought of a better name. The name is a historical legacy from the science. So one of the driving science questions for the Square Kilometre Array was detecting the period of cosmic history where the first stars and galaxies were born. And it's known as the epoch of reionization. And quick potted history of the universe is that you have the Big Bang, universe inflates, eventually becomes cool enough for photons to decouple from matter, and you get the cosmic microwave background. And then the universe is really, really dull for a long time. There's nothing but neutral hydrogen. And we call it the Dark Ages. And then eventually, stars and galaxies start to be formed through various processes, and they ionize the hydrogen. And that's when interesting stuff starts to happen. But exactly when that happened and how it happened is still an open question in astronomy. We have some constraints, but we really need a clearer picture of what happened. And so that was the first driving question for the Square Kilometre Array. And the reason behind the name is that someone worked out that you would need a square kilometre of collecting area on your telescope, which is, see, even other astronomers are going, so that's where that comes from. Yeah. Because the sensitivity of a radio telescope depends on the collecting area, the cumulative area of all the dishes that you have in your array. So square kilometre was what we needed. In fact, what we've built is way more than a square kilometre, so it's better than what we first planned, because that was a while ago. Thought of other things we might want to do since then. But the name has remained, and it's just, and it's always going to be with us.
I think Square Kilometre Array has I could see that on a poster for someone playing Blackpool, and they're joined by Square Kilometre. It could be worse. You could have named it after a famous man, and then we'd have found some letters from him years later and gone, oh dear, we're not going to name it after that famous man anymore.
You talk about a band playing with that name. If you Google Scar, right, astronomy is not the first thing that comes up, surprisingly.
Oh yeah, that is
universe
true.
got a lot more interesting in the 70s.
So yeah, it's also not good for brand recognition.
Now, Laura, we're going to get to gravitational waves, which is,
Yeah.
again, this is something that I would say of all the subjects we talked about in terms of public imagination. When the stories first started coming out about what was going on, no one had any idea that this, it's the most remarkable, and I think to many of us, the way that we would view the universe it's a counter-instinctual understanding. And so tell us a little bit about how important it was to detect gravitational waves and what that process was, which again is, when you start hearing about this, is just truly remarkable.
Yeah, no, absolutely. So gravitational waves are a brand new spectrum to look at the universe. Up until 2015, we've been looking at the universe through the electromagnetic spectrum. So that's akin to your eyes, if you will, whereas gravitational waves are akin to your ears. So there's a kind of like a different sense, if you like, of the universe that we could actually start detecting if we could detect and see what gravitational waves were coming from. And so, yeah, that's what we've been setting out to do for a blinking long time, if I may say so. So the theory obviously started with the main man, Einstein, and it was like 100 years after the fact that I think we got, if you like, clever enough to build the technology to actually be able to find these things. So if you could actually go to the ripples in space-time image, please, Harry. Thank you. So gravitational waves are defined as ripples in the fabric of space-time. Now, you might not think about space-time a great deal. I think about it all the time, obviously. But you want to think of it, if you like, of a massive trampoline, okay, and it's bendy, okay? And this is the fabric, the substance that kind of fills us all of the time. Now, if you move through this substance in a very similar way that a boat moves through water, you'll create ripples in the fabric of space-time. Me just waving at you right now, I will be producing ripples, and they'll be traveling, hopefully, well, typically in your kind of like general direction in a very transversey kind of way. And this is just kind of showing you this image, this kind of like rippling in the fabric of space-time produced by a binary system of some kind. So let's just say this is two stars orbiting around each other. Now, gravitational waves are extremely, extremely weak. This is why it took us so long to actually find them. My colleagues here, I think, have the luxury of being able to create their sources in the lab, for instance. You smash some particles together, you can look at what's going on. Although it's not very interesting for you, I could create radio waves and you could detect them, but not for what you're doing. Yours is way more exciting. But, we can create radio waves. Whilst I'm saying that I can wave my arms at you and create gravitational waves, if I built the biggest gravitational wave emitter on Earth, I would still never have the chance of actually detecting them. So I'm totally at the mercy of nature for detecting gravitational waves coming from out there in the cosmos. And so the idea came to actually try and find neutron stars that are colliding with each other, way back in, I think, the 60s or something like that. We knew that pulsars existed from research with Jocelyn Bell-Bonnell and various other amazing folks at the time. So we knew that neutron stars spinning were a thing. Two of these things spinning and then crashing into each other should produce an enormous amount of gravitational waves. And so this was something that kind of inspired LIGO, the Layers Interferometer Gravitational Wave Observatory. We knew those things should be out there. We got a targeted instrument to find those things. So could you go to the picture of Livingston? Thank you. So this is my telescope, and it isn't a traditional telescope in any sense that you're kind of thinking with like the radio and stuff like that, lovely George Roll Bank. My detector is a massive L shape. It's an interferometer, okay? And what I'm doing here with this interferometer is trying to measure the stretching and squeezing of space-time. So if I wave my arms at you right now, gravitational waves are going through you right now. And let's just say, if they were really, really strong, this is what would happen. In one part of the wave, your height would increase, but you would just get a little bit thinner, let's say. Perfect. And then in the second half of the wave, you'd get a little bit shorter and a little bit wider. So there's kind of like plus this stretching kind of effect that you will actually see with these waves. So with an L shape, what I'm looking for is, if you like, as a wave is coming through, one arm to slightly increase in size and the other arm to slightly decrease in size. So you're kind of looking for this stretching and squeezing, and you're taking advantage of the L shape here. Now, what I happen to not particularly mention, hopefully the picture is showing you in some kind of scale idea, these arms are 4 kilometers long, a couple of miles. And my point is, if I smash 2 neutron stars together or happen to be 2 black holes together, it will actually cause the stretching and squeezing of these arms at about 10 to the minus 18 meters. So if you can imagine the smallest particle in your body, an electron or something like that, is about 10 to the minus 15 meters, something like that. 1,000 times smaller than that is what's caused when two black holes collide way out there in the cosmos. So as you can imagine, me waving at you right now, you're very, very safe. And I can't produce anything like that here on the Earth. So these are my massive, if you like, a microphone. I am listening for gravitational waves coming from any direction in the universe. I don't point in a similar way that you might do there. I just turn it on and then hope for the best. And that's what we start detecting. And a couple of weeks ago, we turned it back on after doing some upgrades, and we're starting to hear things on the order of every few days, these neutron stars, these black hole signals kind of coming through.
What I love about that as well is I think it's very important in science communication to have an image, which means that an audience suddenly remember what they heard before. And the fact that now that when anyone sees anyone doing jazz hands, they're going to be thinking about gravitational waves.
That's it, awesome.
Has improved jazz for me, no end.
Oh, I'm happy for that.
But what, just if gravitational waves had not been detected,
Yep.
and I realise, this is basically, as you said, this is almost 100 years,
Yeah.
isn't it, of going, we need to find the technology to prove something that is down on paper,
Yeah.
we don't know how to do it. If it had turned out, how does that change? What do we lose in terms of our perception of the universe? Do we see equations suddenly disappearing? Do we see the work of Einstein becoming entirely null and void, or merely, some of it disappearing?
Yeah, so I remember, when I joined this experiment, if you like, back in 2009 when I started doing my PhD, this was the point where we kept telling funding agencies, we're going to see something soon, just keep giving us some money. And secretly we're all like, we don't really have the sensitivity, but they don't know that. There was a point, though, that when we went down in 2010, we had 5 years of upgrades to create these instruments that we have here to really jazz up the sensitivity. And the question did come up, or at least several of us did ask this who were kind of new to the field. How long do we have to be on and we don't see anything for us to go, oh, that's interesting? Because we were super lucky. We turned on and, pretty much within a few weeks, the first detection came through. And this was before a science run happened. We were just tinkering around with the instrument just to check that we knew what we was doing. So those questions very quickly went. But yeah, I think the story was about a year. If we'd ran for about the order of a year and we hadn't seen anything, that's when you start getting worried about general relativity. Because there should be some gravitational waves there. They should be traveling at the speed of light. If we've understood the theory right, that's what should happen. But I think, to be honest, if we hadn't detected them, people had probably looked at the instrument first rather than chuck away the theory. I think, given all the other ways in which general relativity is being correct, and we appreciate that it's good on the big scales, not necessarily on the little quantum scales, people are very loath to get rid of it right now. So I think we would have probably started pointing at the instrument going, maybe we're not as clever as we thought we were.
Wouldn't we have had to give up on conservation of energy as well? Because there were binary systems we'd observed that were actually losing energy.
Yeah.
That would have to be gravitational waves.
And if they're not, what the heck is it?
Where's it going?
Yeah, no, absolutely. Yeah. So there's a lot of things that were riding on it going, we're pretty certain this has to be there. And it's just, did we actually understand our technology enough to actually create this?
Yeah. But that's what I wonder, Sarah, there is that both Jon and Laura were talking about the fact that in both those experiments, the LHC and in terms of detection of gravitational waves, we were lucky. Is that really just that kind of, humble? Because it seems, that's two big bits of luck if that really was just luck.
So maybe I'll go with the Higgs to start with. I mean, although we had not yet discovered it at the point where the LHC started taking data, because it plays such a fundamental role in the theory in the sense that it explains how other particles acquire mass and how some of the forces behave very differently at the energy scales we look at them, even though you can think of them I love the image changing. Even though when you go to higher energy levels, you can unify them into a single interaction. So that model where you have the standard model, we have our fundamental forces, we know the particles that make up matter, that had been tested to immensely high precision in the predecessor to the LHC, the Large Electron Positron Collider. So you could kind of do sort of precision fits your data, assuming the Higgs is there, and say, well, what sort of mass ranges for the Higgs boson are we favouring, and could we then discover it? So I wasn't there when it first switched on, but at least the feeling I got is, people were relatively confident that if the Higgs did exist, we designed our machine such that we could find it. And actually, this is one of the big challenges we have now with trying to design our future experiments, if you don't yet know what we want to try and find. So that's why, in the spirit of exploration, what we need to do is try and design our experiments so that we can explore a rich, different range of phenomena and access potential new particles that we want to uncover. So I'd say, we were lucky in the sense that we found it quickly, but when you design your machine, you say, well, we want to be able to discover this new particle or measure this process very precisely. And, the LHC had been designed such that it would either uncover the Higgs or discover some other new, rich, exciting phenomena that would be needed to explain the things that the Higgs was in the standard model for.
John, how important is it in terms of, thinking of financing these things? These, as we mentioned already, these are enormous projects and very often things which the majority of the public have no idea are part of their world or their universe. Does framing the question that you're saying you're asking, how much does that play a vital part in terms of trying to get finance, and how true is it very often that is actually what you're doing? Because I know that we've talked before that it's actually very often a much broader exploration, but you have to try and thin it down so that people go, no, that sounds like you're going to get an answer for that, and we'll give you some money.
Yeah, I mean, it's you need a diversity of these things in reality. So, and to build an experiment for one goal is quite rare, right? So in gravitational waves, it's true, the goal was to discover them, but now you do astronomy with them, and there's a whole hinterland of new science they're doing now with gravitational waves. Now we know they're there. And the Large Hadron Collider was, find the last piece of the standard model. Okay, it's not. I mean, it sounds like the end of the story, and like any other discovery, it's not. It's the beginning of a new story. And the fact that we've got into this new territory where we're above this scale that Sarah was talking about, where they call it the electroweak symmetry breaking scale, but it's where the fundamental particles acquire mass, and it's where two of the fundamental forces unify. So physics above that scale is very different from everyday physics, and now we're exploring that for the first time. So it's nice to have a kind of elevator pitch for what it is you're trying to do, but it's always fraught with danger because, one of the things was, we'll find supersymmetry, and it's not there. Well, it would have been a total failure if we'd found supersymmetry and it wasn't there. What we've done is your experiment works, and it tells you have to be a bit humble about nature. So you talked about humility or modesty. The humility you need is in approaching nature. Right? You build an experiment, you hope it works. You're not shy about that. You do your best to make it work, and you can be quite proud of the technological achievement. But if you went looking for something that isn't realized in nature, then that's not a failure. That's you found out something new about nature. It wasn't what you hoped, or it wasn't what that theorist had predicted, but it may be something else. And the idea that if we didn't generally, in the end, discovered that gravitational waves really didn't exist, having gone and debugged the detector as much as we possibly could, or that the Higgs didn't exist, as Sarah was saying, either of those would in the end have been profound new knowledge about nature, and the experiment would have worked. And sometimes we frame our elevator pitch that they would sound like failures. It's like, wouldn't have been a failure to not discover the Higgs if the Higgs didn't exist. In fact, if it didn't exist, it would have been a huge failure to discover it, but it wasn't there. So it's that kind of humility of approaching nature. Right? There are two things. There's the ambition of building the thing, and if the experiment is well posed and looking in interesting regions, the very fact that they're interesting regions means that actually you can't really know what's there. You have ideas, but you don't know, and that's why you build the experiment.
Anna, is that something like philosophically that way that we look at these huge experiments, and some people just want to know an answer, and yet to me the interesting thing is the journey. It's like with, I was thinking of Twin Peaks when they found out who killed Laura Palmer. A lot of people stopped watching because they thought, well that's it, that's all we were waiting for. Whereas I then went, oh wow, this world keeps getting more and more fabulous. And so that bit of our changing of our philosophy into not just about science, I suppose this is on everything. It's going, this is the interesting bit, which is to be able to keep generating questions. And as you said, John, no one went, we found out about the Higgs boson, we might as well turn all this thing off now and just turn it into underground flats,
Actually, some people did say that.
Yeah, I think it's a really nice way to describe it as a journey. because especially when you're building these huge experiments, they don't happen overnight. It's not like you decide to build it and 3 weeks later it's there. Like, it takes decades. And during that time, you change your original question, you discover new things, your ideas evolve, and the evolution of those ideas is influenced by that journey that you're taking to build the experiment in the first place. So there's a lot that goes on that is completely parallel to the original question that you perhaps wanted to answer. And even once you've built the experiment, as Jon said earlier, it's not just about that single question that you perhaps designed it for in the first place. Your new facility has opened up a new regime of phase space where there are a whole bunch of new possibilities. And the most exciting things are the things that you hadn't thought of, the really serendipitous science that can come along the way. And I think that it happens on multiple levels, especially for these huge facilities, because there are the scientific questions, and then there are the technological advances that you need to make in order to answer those questions. Because when you are trying to detect the new regime of physics, when you're trying to detect the tiniest elements of our universe, or whether you're trying to visualize the big picture of how the universe came into being in the first place, you're really pushing the boundaries of what is technologically possible in a way that you don't need to do for more mundane reasons on Earth. And so the technology that you produce along the way also advances. And I mean, in reality, you know, in terms of the money that's used to fund these facilities, certainly at a governmental level, that is realized. Right? The science is not necessarily the primary driving factor. It's what the science will produce.
Well, that's it. And Laura, I wanted to ask you about, with gravitational, one of the things that sometimes I think there is a nice idea that scientists are all very objective people and they all just sit, that. But of course, as we know, there's subjectivity there, there's emotions there, there are egos there. Mm-hmm. And I imagine on projects of the size that we're talking about, that trying to corral all that, or when you get the first results on gravitational waves, and then where do you go next? Those kind of meetings. How much is that a problem, and how much does that, the enormity of the number of people involved, also increase the possibilities of ultimately better answers and better questions?
Yeah, that's absolutely fun. It takes a village, at least, if not a city, to kind of do some of the science that it is that we're doing. So quite often I say that, today I'm working with, all my close friends and family happens to be on the order of 1,500 people. It takes that number of people to actually detect and to keep measuring gravitational waves, from the folks who built the instrument, to doing the daily commissioning of the instrument, to the folks that are designing the data analysis pipelines, the folks who think of the theory behind it, and, et cetera, et cetera, et cetera. So it does take a whole range of people thinking about very different things. When I go to the sites, it always keeps refreshing me that they're thinking of the engineering questions. And then I always go there and talk about the science questions, because obviously I'm coming at it from a different angle. Whereas they're like, well, what can I do? What can I tweak so that you can find, say, more black holes or something like that? And I was like, oh, you don't really care about black holes, do you? It's like, no, I want to make this instrument as best as I can, kind of thing. So it's kind of coming at it all from different angles, which I think is just interesting once you take yourself out of your bubble in terms of like the area that it is that you're concentrating on in the big machine that it is that you've got to be all working on. And like I said, we need all these people, but it can be sometimes a bit tricksy focusing people in all the right kind of different directions and stuff. Because there's certain things that need to get done, right? Like I need a detector, it needs to be calibrated, I need to make sure the data quality is right, and then I can do the science. But quite often it's the least amount of folks that are doing those little critical things to enable the rest of the science. I might have about 100 people that want to test general relativity in all sorts of weird and wonderful ways, but if you don't have more of me looking at, well, if I don't get rid of this weird thing in the detector, then you're not going to be able to measure that part of the gravitational wave frequency space. And that's really important. So it can be tricksy trying to motivate, I think, people to do, if you like, some of the more fundamental bits of the science it is you're doing to enable some of the more big picture, sexy science and things like that. So that can be a bit of a challenge sometimes.
Sarah, what do you think are the biggest issues that you face in terms of projects of this size?
Oh gosh, I mean, that's a very good question that a lot of us have been discussing this afternoon. So one of the challenges we have in particle physics now is the experiments we're wanting to build basically go on longer timescales than a career. So, if you think about the LHC, the idea of putting a hadron collider to collide protons in the tunnel that the Large Electron Positron Collider was in, that was first proposed in, 1984. It was then approved in, here we go again, in 1995 and saw, first collisions in 2010. So, we're currently debating a number of options for what we'd like our next experiment to be. One of them, and this is in keeping properly with the theme of the not necessarily best naming, is called the Future Circular Collider. So if any of you can come up with an F word that could go in front of Circular Collider so we can keep the same logo, that would be excellent. Yeah, I guess it's possible. Because hopefully, if this project ever did become a reality, we don't want to call it the Future Circular Collider anymore. So this...
Or the Future Underground Circular Collider, either.
Yeah, I did admit I...
Sorry. I just had to drag it down for a moment. I felt it got...
No, that is fine. I mean, it is going to be under the ground. So the idea is that this would be, it's kind of the go big or go home of circular colliders, basically. So you take a 90-kilometre ring, that would have to go not just underneath Lake Geneva, but also tunnel under mountains, and we could use that first to collide electrons and their antiparticles, the positrons, together, and that would actually allow us to make really precise measurements of the Higgs. It would be called a Higgs factory. So, the LHC was designed to discover it, and now we're thinking about machines that would allow us to make, billions of these particles so we can measure them to very high precision. And then, that could run for, say, 15 years, and then we'd change our accelerator, and we could then use it to collide protons together at 10 times the energy that what we can do in the LHC. So, if you look at the possible charts for how these experiments would map out, so our giant proton collider, so the successor to the LHC, which would enable us to kind of explore, if you go back to Jon's idea, explore further frontiers.
Build a bigger boat.
Yeah, bigger boat. You can think about it like that. That wouldn't be taking data until 2070. So, as a community, we have to plan and prepare for experiments that many of us wouldn't see taking data, and that's I think that's a big challenge in terms of checking that everyone's enthused by the challenges and the journey we have ahead. We have to be aspirational with the technology in the same way as what happened for the LHC. We have to say, here's what we want to do. Here are the magnets we would need in order to do this. Can we go away and do it? So, you have to both set kind of ambitious goals for what you want to do with your physics, and then you have to actually establish if we can make the technological developments we need to achieve it. And then you have to convince everyone it's a good idea, find the funding, which, again, as these experiments get bigger, the costs go up. And also, if you're going to even larger circular colliders, we need to actually think about energy efficiency, how can we do these without, completely maxing out the French electricity grid, which, again, lots of challenges. So I think it's an exciting road ahead, but there are lots of things we'll have to overcome to get there, and I, hope in 50 years' time I'm kind of sitting watching, basically.
Jon, bringing up there the finance of it, and of course, again, quite often in the mainstream media and in social media, there will be people who say, "I can't believe they're spending this much money," because it's quite often science is framed as almost being this kind of just an esoteric thing. So when someone does say, how do you justify spending all this money? What is your, and this is when you're still sober, this is before you've had a few drinks. What do you, what's your first comeback?
I think the answer is very simple, that they make money. So they're a good investment. And even if you don't, the Higgs itself hasn't made money, but if you do any kind of investment analysis of the expenditure on CERN, it has been of huge economic benefit, not just to Europe, but to the UK and to the rest of the world, in fact. So, and this comes from all kinds of mechanisms in there, a lot of them from the people you train, in fact. But also, the industrialization of superconductivity, the technology, the fact that they're big public investment projects, which in the end pay for themselves on any reasonable, more than pay for themselves on any reasonable calculation. I think that's not the whole answer, though. That knocks the kind of economic thing on the head, if you like, and puts it in context. This is an investment that you'll get a return on. right? And then the return is not the Higgs boson. I'm talking about money. I think the more complicated thing is that there's an opportunity cost, right? There are more good investments that you could potentially make than you can make. And that really then does come down to the science. And it also couples with the way you actually make money out of these things, because the reason something like CERN or gravitational waves or SCAR make money is...
Do you see the way he did that there? Yeah. You'll see a little bit of animosity now.
No, it's good. I like SCAR. The reason they are successful, actually, to a very large extent, is where you came in at the beginning about the inspirational value they have, and what they put out, the way they motivate people to become more than the sum of the parts, and to pull in people to science and technology subjects, and the sense of wonder and things, which all is just generally positive and has huge societal benefits indirectly and directly. That doesn't work if the science is boring. If you're just building another bigger collider because you can't think what else to do, and it's actually not very good, then you won't get the economic returns. You also won't get the people to dedicate their career and beyond to working on it. So the economic argument is, in a way, a bit of a blind alley. If it's good science, it will make an economic return, and that will be fine. The real question is it good science and technology, and is it technologically achievable? Will it work?
The answer is yes, by the way.
It's definitely good science. The technology, we have to do some R&D probably. But the way the question is phrased, the simple answer is it will make money, but then so will lots of public investments. And it will not make money if it's not good science, and it will make you'll get more economic benefit and societal benefit and the rest, the better the science is. So the correct discussion is how good is the science, and what could you be doing instead? And would that be better or not as good?
But it does seem to me, it's a bit like when people say, what's the point in libraries or something like that, which is going, the point in libraries is because that's what civilization should be about. It's a curious population filled with questions, filled with different possibilities, filled with stories, makes for a much better society as a whole as well. So it feels, I mean, Anna, do you ever have to deal with people, again, coming up to you going, oh yeah, this is spending a lot of money on all this, aren't they? What's the point of that, just looking out in space?
That's my dad. In exactly the same way that Jon described, is big scientific facilities of any vein face the same questions, right? Because people see them as a cost often when they, as Jon said, they are an investment. And I think astronomical facilities, especially if the science is exciting, and astronomy is a particularly visual science, so it is very accessible in a public way, really do have that inspiration factor. I think astronomy often gets described as a gateway science. You come for the astronomy and stay for the physics. And it's underestimated the return that provides, I think.
And Laura, in terms of general, I feel, we were talking about this beforehand, sometimes I'm very optimistic and positive about the majority of the public's attitude towards science. Mm-hmm. And then sometimes you spend too long on social media, or you accidentally watch the Joe Rogan show, and then everything goes a bit awry. So I just, wonder, how do you feel in terms of that sense that these big projects have infuse people, that when people see some of the images, when people sometimes even when they hear ideas about gravitational waves, and they may well not even be fully grasping what that means, and yet just the magnitude of the endeavour is so great that you can't help but feel like this is almost like looking at the Grand Canyon. It's such whoa, it's just an emotional reaction. Do you feel this has helped, the big projects really do help infuse people?
Yeah, no, absolutely. Occasionally there is that, what does this cost and things like that, and like you said, I can come back with, well, everyone in the US has bought me a cup of coffee or something like that. That's basically how you fund LIGO, which doesn't sound like a great deal, but they may not have bought me a cup of coffee. But usually that's really small in comparison to just the next question of, so what is it that you do? And I get to say that I look for black holes for a living. And then you forget about the rest of it, and then it's just, how the heck do you do that? Or what have you found out so far? And it just comes back to that kiddie imagination, like you said, like looking up in the night sky, like what's out there, and everyone's just I've never found anybody that isn't into it. Fair enough, they might not like my brand of astronomy or astrophysics quite the same way as someone like, CERN or something like that. Everyone has I like that more than that. But I've never kind of come across against any hostility in kind of it. I think I remember realizing just how big gravitational wave was, or the kind of imagination that it sparked was the day that we announced the first detection. It was back in like February 2016. It took us 6 months to actually get there. And we'd just done a press conference. I was living in the States at the time. And we said, right, we're going to the pub now. We've earned a drink. So we went to the pub, sat down, and then the next minute, the American, like ESPN was showing American football, and they didn't necessarily stop playing the football, but the actual presenters started mentioning gravitational waves, like this first detection's come out and stuff like that. Like, whoa, Americans stop talking about sports, talk about science. We've got something here. And that's just kind of continued and stuff like that. And so yeah, I think there's always that little bit of wonder in absolutely everybody, no matter what it is. You don't have to be a scientist. It just gets you excited.
Well, I think it is also, as you were just saying there, that bit that science should not always just be, we'll put science in the science place.
Yeah.
To find it, whether it's in comedy, whether it's in sport, country, wherever it might be, is that bit where it goes, well, it is everywhere anyway. So why do we keep having to confine it into, the media will very often go, and now some things about science. So you can watch the other side if you want. I think it's really important to do that mixing up. Also, of course, with black holes, I think the fascination with them has been greatly helped by the word spaghettification. The fact that spaghettification exists as a word, that alone means well done, black holes.
I was just going to say, kids, when you mentioned spaghettification, it's just absolutely amazing. And like you said, the name just inspires, like, I know exactly what that means. I'm going to turn it into a string of spaghetti. Awesome. Then you always get asked, how close do I have to get? Like, almost worry then in the next instant. Like, oh my God, am I going to become like a piece of spaghetti tomorrow? It's like, no, it's fine, don't worry.
We're going to take some questions from the audience as well. So there's 2 roving mics, and if anyone would like to ask anything on the big projects or any of the ideas that you've heard about, yes, we've got a question right down at the front, and then we'll come to you as well. So right down the front row here, just over on stage left.
Stage left.
Is that what that means?
Yeah.
Okay.
Yeah.
Every day's a school day.
Thanks. Hello. All right, hello there. Hi. So I came here tonight really interested about the 2 theories, relativity and quantum mechanics, and the gap. I'm trying to understand the gap that's between them, and it's really interesting looking at the panel because Robin's in the middle between the relativity and.
They do fight.
So are you the answer, Robin? Are you the thing that ties the two
Or am I
together?
the impediment? Am I the thing that's stopping us manage to get gravity and quantum mechanics together? I mean, that's a very interesting... I remember... I hope I'm picking up on the question that you'd like to be...
Just how close are the 2 theories, and what are the tendrils that are...
Well, because it is such a... Because I remember I've spoken to a few scientists and said the basic point is, in the end, gravity is going to have to go, which then worried someone when I told them about that. And I said, no, whatever is keeping us on the ground is going to remain, but gravity, this is what I've generally been told, which is quantum mechanics looks like that's going to stay, but our understanding of gravity is going to have to change, and we're going to have a new name and a new understanding. Is that fair to say that's...
I think so, yeah. So right now, obviously everything that I'm doing is definitely testing general relativity, and we're always trying to poke holes in it, and so far we're really failing at that. But we do know it doesn't work on the smallest of scales. But I think it's the same way that we had Newton, and what Newton said about gravity. It wasn't quite right. We saw some ways in which it wasn't right in terms of like the orbit of Mercury or the bending of starlight that Sarah mentioned. And then you have to do something, augment it in a way, and you get what Einstein says. It's not wrong, you've just got to add something to it to get it there. So there's something that we've got to do then to general relativity to get it there, or something utterly brand new. And that's where it's exciting, that it's probably not necessarily my experiment that's going to get there with it. I'm thinking all the folks there on the left-hand side with the here be dragons and there goes the quantum gravity kind of side of things.
It's a big ask even for the FCC,
Yeah.
I have to say. Yeah. I think you're the Planck, by the way.
Oh, okay,
in the
fair
middle,
enough.
Planck scale.
Yeah, but I mean that's such a because so that's where we've got to. That's it, isn't it? That is the sticking point when people will say, so why can't we go back to the very beginning of the universe? That's the tiny. And can you just remind us again how when you talk about Planck scale there, how much of a second are we talking about?
Oh, I don't know in seconds, but it's something like 10 to the power of 39 in GeV energy scales. So a lot higher than we're at now.
It's an energy scale. I can't do the conversion.
Yeah.
But anyone in the audience has got the number.
Oh, someone will have it in the
yeah. I mean, it's so early on that it's not really even worth thinking about.
Wouldn't that be great if that's what we got to with quantum gravity? John's just decided it's not even really worth thinking about, so we're going to move on to something else.
To be honest, I am an experimentalist and I have limited patience for speculation about things that we're never going to measure. But I think there is a general consensus that at the moment, I mean, the consensus has been wrong because there's no data behind it, so it may be wrong. But seems to be a general consensus that gravity will have to give. It is probably some kind of emergent phenomena from some other deeper reality. And in fact, black holes are one of the connecting factors because they seem to connect gravity with thermodynamics, which is something that's independent of the fundamental. They have an entropy and things. Right? So I mean, it's way beyond my skill set. I'm an experimentalist, but this is what I'm reading from my theory colleagues at the moment.
We have another question, just one row back. Yeah, we go. Yeah, just keep your hand up to the mic there. We go. Brilliant, thank you.
Thank you. My question is supersymmetry as a theory dead?
Right.
Oh, your way.
Sarah's been looking for it for ages. So.
Having spent quite a lot of time not finding it, I'm still going to say no. But to explain to those less familiar with it, supersymmetry is a fairly popular, it used to be quite popular, theory for beyond the standard model physics, where you say that every particle we know about in our current model, the standard model, has a heavier superpartner. And that can explain some of the known problems with our theory as we have it today. And actually, it's already been mentioned that in the days before the LHC switched on, we were relatively confident that we could even find supersymmetry before we even found the Higgs, if the particles lay in particular regions of our kind of exploration landscape where we would see them quite quickly. So, you could take the fact that we haven't seen any evidence of supersymmetry to date as either it doesn't exist, or if it does exist, nature has chosen a particular area where it's hard to find. Either it's far away, i.e. at higher mass scales than we've been able to access before, or that maybe the parameters of the theory are such that it would look, if we produced it in our collisions, really like things we already know about. So, if you're playing a statistical game of rolling the dice, you say you've only biased your dice by, 1 in many, many billions or something like that. So, yes, I think you might be worried. I don't think it's over yet. But actually, again, this is why we should probably be focusing less on, what we're going to discover, and also just trying to explore all the areas where we could possibly see our theory starting to break down. And then either we will have verified our theory to immensely high precision, which in itself is very good information, or we might start to find cracks that could lead us down the route of understanding what goes beyond the standard model.
So what we're saying is, please write the check out afterwards. Finance is still required for this. Have we got any other questions out there? Anyone else trying to? Yes, right down at the front again.
There's one on stage, right?
Oh, great.
He's gone.
So my question is, what actually is a Higgs particle and what does it do?
Right. So yes, what's it? Higgs particle.
Yeah. All right. This is my job. Right? There's a problem with giving. These are the fundamental particles that you see there. There's a problem conceptually and mathematically in giving infinitely small particles mass, giving them substance. Right? It sounds intuitively tricky, and it turns out that doing that, if you do that kind of by hand, then you break the symmetries in the theory that make the theory work. So it's both conceptually and mathematically a big problem. This was realized in the 60s that this was going to be a problem, even before we discovered half the particles on this picture. And Peter Higgs and Francois Englert and Robert Brout in the early 60s came up with the idea that, we'll make mass not an intrinsic property of the particle, but a property it gains by interacting with a new quantum field that we just made up. And this new quantum field they made up fills the whole universe. Even in the, if you want to get rid of it, you have to put energy in. Basically, it's what we call a vacuum expectation, a non-zero vacuum expectation value. So that even in the lowest energy, most empty bits of the universe, this field is there. And any particle traversing that will have mass because it's interacting with this field, which is a great, neat solution based on mathematics. You know, it's basically to make the maths come out right, you've filled the universe with this new field you made up. And as an experimentalist and as a physicist in general, you would like more evidence than that. You'd like the evidence that these theoretical ideas are borne out in nature. How do you find out whether that field is actually there? It's quite difficult because it's everywhere, so you can't compare an empty bit of the universe with a full bit because it's everywhere. The best way I can think of saying that is, well, a field in physics is just something that has a value at every point in space. So you can think of the air in this room as a pressure field. Okay, you can measure a pressure at every point in space. How would you tell the pressure field is there? There are lots of ways. I mean, if there was no air in the room, you probably wouldn't be paying attention. But even if you were paying attention, you wouldn't be able to hear me because there's pressure waves of how you're hearing me. They're traveling from the speakers or from my mouth to your ears. And that is what the Higgs is. So the evidence the pressure wave is there is these ripples in the air, the sound waves. The evidence, if you want to find whether this background field that Higgs and Brown and Englert made up is really there, hit it really hard and see if it ripples. And because it's a quantum field, that ripple is a particle, and that is the Higgs boson. And that's what the LHC did naively. It hit the universe really hard, made ripples in the background energy field, and those are the Higgs bosons.
So could there be a universe without matter then? I mean, because that's what obviously when we think of a universe, we think of the objects within it.
Yeah. I think cosmologists usually deal with a universe without matter, actually. Because it's easier, right? I mean, you can make it work. I mean, I'm not sure I really understand the question. I mean, seriously, you can talk about the geometry of space-time.
I suppose this idea of the solidity of things is something that we think of as being, you know, when we look at planets, when we look at stars, whatever it might be, that it seems to be a necessity for a universe. So I was just wondering, when you were talking about the Higgs boson, thinking of the possibility of...
It seems like, so if you mean without mass, for instance, so you can certainly have matter without mass. And in fact, most of the mass in the universe doesn't come, well, actually we don't know where most of it comes from, it's that matter. But I mean, the mass we know about, mass of you and me, mostly doesn't come from the Higgs. It comes from the strong interaction, which is a binding energy of the nucleus inside us. So nature seems to like creating, if you like, mass is just a form of energy that can stay still. If you like, nature seems to create that even from massless, even if it starts with massless particles, which the strong interaction does. So I don't know whether you could set up a universe. I mean, if you turn off the Higgs field, right, the protons, I think, would still be okay. Atoms would not, because the electron would be massless, and the electron would not then be bound to atoms. So we would fly. It would be quite dramatic. So don't do it.
I won't. I'm not going to get involved.
But whether you can, I think you can mathematically build a universe like that, but it'd be quite. It's not clear you'd be here to build it.
It's worth saying that very, very early in the universe, before the Higgs field took on the state that it has today, the particles that interact with the Higgs were massless. Yeah. So it's something like, I think, the first 10 to 12 seconds of the universe before the Higgs field took on the vacuum, the non-zero vacuum expectation value it has today. Then it was in a different state and everything was massless. And actually, the nature of that transition, there was a question earlier about, where do we meet in the kind of GR versus fundamental particle physics? But actually, the impact that the Higgs field could have on the behavior of the early universe is actually an area where I think astrophysics, high energy physics, and cosmologists will start to be able to kind of coalesce and answer the same questions in the coming years. It's quite cool, but a bit weird to imagine.
Thank you. We had a question down. I don't know where the mics go. We'll take that one just there, or should we just take that just because you're there? And then we've got one right at the front as well. So if you want to come down with the mic there, we'll go straight to that.
Hi. Apologies if this isn't kind of the remit of the talk. I went to something recently that talked about parallel universes. I wondered if any of you had any thoughts on that, if any of your work shed any light on that. I might get the number wrong, but theoretical physics, maths, 11 universes. I'm just really curious.
So, parallel universes. Because
Sorry.
there is if anyone, I suppose we've got the parallel universes, then people hear about multiverses, then people hear about many world theory, and I would imagine that all of those can very easily get kind of conflated in public imagination.
Yeah, no, absolutely. Like it's kind of like you said, where can your imagination go to kind of like think about all these kind of different scenarios? There's plenty of research out there, or at least folks that I know that are thinking about these different things. Brain theory and brain world theory and things like that. Folks that are definitely thinking about the multi kind of verse, kind of that kind of stuff. I guess everything that kind of like I kind of been thinking about is, can I test it? Almost like, because your imagination can take you absolutely anywhere, right? So obviously you can think about all these wonderful kind of scenarios, but will we actually ever be able to test it? Will we ever actually be able to know about it? And I think that's the next thing, because otherwise then sure, we can come up with everything. It would be awesome. Testing multiverses? Not sure about that. Maybe some of my other colleagues here have got a better answer than I have about that. But yeah, so folks are definitely thinking about it. I'm not too sure if it's ever, if you like, going to come to something that will be measurable in that sense. It's exciting though.
It's great for Philip K. Dick novels.
Oh, it's great for novels.
That's one of the things, isn't it? It's still got its purpose.
Oh yeah.
Anna, would you like to add anything?
I have nothing to add on this.
Very much. We've got a question down at the front there.
Super, thank you. I once heard that the universe is expanding into the future, which I thought was a fascinating concept. And I wonder if anyone could elaborate a little bit more as to what is the universe really expanding into?
Right. Oh, I like this moment.
Yeah, no,
I'd like to go with that.
This is the bit that I think blew my mind when I was kind of like first trying to get to grips with cosmology and stuff like that. And when I say get to grips, I can't claim that I've got to grips with it yet either. It's just something that we're constantly thinking of. But I think probably what you're kind of getting at here is that right now we've got an observable bit of our universe, and we can see, if you like, to the edge of our kind of like wonderful little sphere. But then as time goes on, obviously the space that we can actually see is actually increasing. So we can see beyond that. And so if you like, places that were disconnected, or galaxies that were disconnected, if you like, outside of the observable universe, might become within our sphere and become, if you like, causally linked with us, so we can actually communicate with each other. Right now, this bubble is kind of like, the sphere is about the size of, 13.8 billion light years across, or something like that. It's the time that it's taken light to travel from, if you like, the Big Bang. But when the Big Bang happened at all points in space at the same time, it's like you said, where's it kind of going into and stuff? So yeah, I guess the way that I think about it, and I may have it completely wrong, is just kind of like infinite space. We can see this part of it, somebody else might be able to see this part of it, and then one day our spheres might actually come together to be able to actually talk to each other on other sides of the universe or something like that. I'm honestly not too sure. Like the idea that it's moving into something blows my mind, because obviously what is that?
I quite like moving into the future is a nice, because
it's a really
by
nice way of putting
removing,
it.
because I think it is, it's a very again, we were talking about this beforehand, this thing that our brains are not necessarily evolved to go, because that we think that everything has to be within something. And that idea that there is nothing else, the universe is everything, and you know, you're always, the child's mind and the adult's mind is always going to go, but what's on the other side? And so I think yeah, there's a lot of beauty in thinking of it as expanding into the future. And then of course we get the block universe as well, where we've still got the past there.
Yeah.
But anyway, let's not.
There's another cool thing I would just add about that. The picture you just described is that these new bits of the universe, that if you think everything travels at the speed of light, would not have been causally connected before, kind of look the same, and it looks like they have become in equilibrium. They have the same physical laws, they have the same rough distribution of galaxies and things. They look like they've been formed at the same time in equilibrium, so they were causally connected at some point. And this is, I think, where the idea of this inflationary period of the universe comes from, where everything suddenly, there's a period in the universe's life, which some people, in some models, is even kind of, what is the big? It's the bit before the Big Bang almost, where everything expands super quickly, is kind of homogenized, and then dumps itself down into matter, and that forms. So the universe expanded faster than the speed of light, but nothing inside the universe travels faster than the speed of light. So you can then have these new bits that we keep seeing. They're the same as the old bits because they've been in touch with each other before.
Mm-hmm. So. I've got a question down there, I think. Yes.
Hi. Do you think quantum computing also has a big part to play in some of the in answering some of the bigger questions, because there does seem to be some overlap?
Quantum computing, who'd like to, Sarah?
I mean, I can say yes. It's very cool. And I think, the possible applications of quantum computing in, say, high-energy physics is something that lots of people are starting to think about. I'm not, so I can't say much more than that. But, I think it's very exciting to me as well. So, I mean, quantum entanglement and the ideas behind it is something that I, studied as an undergrad and thought, wow, this is kind of spooky and weird. And the fact that we're actually getting to a point where we can kind of harness some of this, I think is really cool. I don't know if anyone else wants to say anything else.
Well, my husband is actually trying to build a quantum computer. So we've got a really fun household. He looks at the very small things, I look at the very big things. And when I ask him about this, can it actually be any useful for what I will do one day? And he keeps saying to me, absolutely not. So I'm like, I would have thought, the sheer computing power or something like that would really help me out. And at least at the moment, I think the way that the current quantum computers are being designed are very specific algorithmic kind of issues, which isn't necessarily what we're doing yet. So I would hope that in the future it becomes really interesting, because I would think so. We take up a heck of a lot of computing power doing what we do. So, but it might not be like, if you like, the next kind of like horizon. We might have to wait a little bit for quantum computers to develop, if you like, into a multi-purpose kind of like platform versus I'm going to target this problem kind of stuff. At least that's what my husband reckons.
I'd also broaden it a little bit and say actually quantum technologies in general are more than just quantum computing. Mm-hmm. And what they have in common is that we're understanding how to build large-scale coherent quantum systems. And you can build incredibly sensitive detectors that way for looking for dark matter. There's even much smaller gravitational wave detectors, possibly. And I think that's a very exciting frontier. And I would characterize it as understanding the physics and the engineering behind making big, large-scale coherent quantum systems, some of which will be computers and some of which will be detectors and other kinds of sensors.
I think we've got time for one more question. Yes, just there's one just right back there, about middle. Keep your hand up just so they can see where you're there. Thank you.
Hi, I hope this isn't too philosophical, but I wonder if y'all interpret the results of quantum mechanical experiences or experiments as incompatible with determinism, or if the general consensus is that the universe is fundamentally random or deterministic still. I'm interested in what you guys think about that.
I just think that as a final question, I am so pleased that we're now going to be here till at least midnight. So that's a great... So in terms of, does quantum mechanics confound the idea of a deterministic universe? Look at all of your faces. Look at the whiteness of your eyes.
Do you want to go?
Who wants to have their first go?
I'll go.
And then, go on then, Jon. If you're...
Yeah, go for it.
I think it's not just quantum mechanics, it's chaos theory. I think between them they mean determinism has no physical basis as far as I can understand, because if you can't predict when an individual atom is going to decay, and then you can't, and that can in some systems have unpredictably magnified consequences, then I don't see how you preserve any idea of determinism. This is me speaking as a guy, not as a physicist. That's the way I see it, and I might be wrong, and I'd be really happy to discuss it, but probably over a drink.
Would anyone else like to have anything?
No, I'm happy with that.
Well done, Jon. Everyone's very pleased with that answer.
This is the drink thing we got.
Oh, thank heavens, this is just a blip of a Boltzmann brain of existence, and none of this actually happened. Thank you very much, everyone, for coming down. Thank you for coming to the Royal Society tonight, and thank you for everyone who's been watching at home, or wherever you work, where you're pretending to work and actually watching this. And thank you very much to our fantastic panel. I think these big projects, I hope they inspire you to find out even more about, firstly, why they really are worth our time, even for us to then understand our time as well at the same thing. So thank you very much to everyone. Thank you to Harry Cliff for organising it. Thank you, Robert. Is that all right?